Okay, so in the last class, what we had discussed, we tried to derive the screen effectiveness or screen efficiency. And what we have seen that screen effectiveness or screen efficiency depends on two major factors. One is the recovery of desired product, another is the rejection of your undesired material. And then we made a overall mass balance and a species mass balance of materials fed to a specific screen. And then we have also seen the specific way the recovery and your rejection is defined, and the mathematical expression of the entire thing, and then everything we had incorporated into the expression of efficiency, which is nothing but the multiplication of this recovery and rejection, and then we finally got an expression of the screen effectiveness. So that is what we had discussed in the last class. And before the last class, we had defined what is the sheaving, what the sheaving process is, what is the difference of sheaving with the industrial screening, and we had also discussed how we define the aperture and what is the standards way of defining mesh number in international standard, in Indian standard. So all these things we had already discussed. So using most of the concepts that we had discussed in last couple of classes, we will try to solve few problems. So you just have your pen and paper with you, so that the small calculation you can do it on your own and recheck. The major big calculation I'll be doing here in the slide itself. So the small calculation you can do. So let's start with this problem. So listen to these problems, because you can expect problem from sheaving in most of your exams. Okay, so what is this problem says? It says that anthracite coal from a pulverizing unit has been found to contain an excess of fine material 75% by weight. So you have an anthracite coal which came from a pulverization unit and which has found to be contain fines, excess fines, around 75% of the entire weight was fine. Now the goal is to remove these fines, and for that we will be using a screen which is of 1.5 millimeter aperture size. Now what we have to do, we have to estimate the effectiveness of the screen from the following data. Right, so the data that is given is the average particle size, oversize from the screen, and undersize from the screen, the relevant mass fractions. Okay, so what do you understand from this problem? So we understand that we are given a sample which is nothing but an output of a system or of an unit, pulverization unit, which the sample is coal, which contain fine materials, around 75% is fine, and we wanted to remove these fines, and for that we will be using a screen which is 1.5 millimeter of aperture. Now what data is given in the table? The average particle size, oversize from screen, undersize from screen. So what do you understand by looking into the table? What data is given here? So what is the first column stands for here? The second column, oversize from the screen.
Product.
Yeah, that is a more matured answer. But what do you understand from this oversize of the screen? How we got this data or this column itself? So to construct this, yeah.
So basically the mass fraction which is having a size greater than the screen's aperture. So
no, if I talk about oversize from screen and this column itself, how you can construct this column, this and this average particle size versus the mass fraction of the oversize from screen. Remember when I defined the screen effectiveness, I told you we have to do something else to get the distribution of your feed, product, and your reject. So this is one stream coming out from the screen, which is the oversize from the screen. So you have a screen, the feed to the screen is whatever coming out from this pulverization unit. Now feed will be fed to the screen and it will be divided into two parts. It's a single screen. One is oversized from the screen, another is undersized from the screen. So once we take the entire mixture that came out as an oversize from the screen, then how we can get these data from that mixture? Okay, let me reframe the question. We have only one screen, 1.5 millimeters screen. So how we are getting this many data?
Sir, seeing analysis.
Yes, so this is what we are doing. We are taking the oversize that we have obtained from the screen and we are doing a sieving analysis. And once you do a sieving analysis for all the oversized particle that you obtain from the screen, you will get this column. Similarly, if you do the sieving analysis of the undersized particle that you obtain from the screen, you will get this column. So you should appreciate that these two numbers are absolutely not related to each other, because this column you obtain for a different sieving analysis and this column you obtain from a different sieving analysis. So never try to correlate these two numbers. These two numbers are not at all related to each other. It's the same sieve that you have used to do the analysis for oversize as well as the undersize. That's why you have the average particle size range as same. Here, is that clear? You might get confused in some places, so that's why I wanted you to ask questions to know that where you get confused. If you get confused anywhere, just stop me and ask me. Okay, so let's note down few of the points of this problem. First, you tell me what is the product here, undersize or oversize?
Oversize.
Why you are saying
Undersize.
oversize? Okay, good. One oversize, one undersize. So the person who is saying oversize, you say why you are saying oversize.
So the question says, in order to remove these fines, like maybe the finer particles are what we don't require, the coarser ones.
Okay, good enough. And what about the logic behind undersize?
In order to remove the fine particles, so I took fine particles as a product.
No, the first answer is correct. So our objective is to remove something. So when we try to remove something, so that is not our product. What we try to retain is our product. So that's why oversize is product here, and what we wanted to remove is the fine material. So that's why oversize is product here and fine is the reject. Right. So the objective of this screen is to remove fines. So undersize should be the reject and oversize should be the product. The aperture of this industrial screen is 1.5 millimeter. So our desired product size should be oversize of 1.5, and how we designate that? We designate that using a plus sign before that. So it's plus 1.5 millimeter. So that is your oversize. Right. So we are defining two variables. One is xp dash, another is capital XR dash. And we define this as cumulative mass fraction corresponding to the particle size of 1.5 millimeter. Question: xp dash and xr dash, will it represent the mass fraction of the desired product here? Let's be more precise. xp dash, the way I defined xp dash, is the cumulative mass fraction corresponding to the particle size 1.5 millimeter. Right, now our product size is whatever product that is having a size more than 1.5 millimeter. Now, will this xp dash represent the mass fraction of our desired product? Yes.
So then that part in the question where it was written 75%.
75% is with respect to feet, and xp dash and xr dash we are defining as the cumulative mass fraction corresponding to the particle size 1.5 millimeter in the product stream and in the reject stream. P stands for product and R stands for reject, and 75% is for the feed stream.
Okay, sir.
Now you answer whether this represents, whether xp dash represents our desired product, mass fraction of our desired product or not.
Yes, sir.
Okay, anyone else? Just check the last class and you tell me what do you understand by cumulative mass fraction.
So I think no, because cumulative mass fraction is, I think it starts from 0 till 1.5 and we need to remove the finer particles, so it will be a mass fraction of undesired.
Okay, so when we say that cumulative mass fraction of particle size 1.5 millimeter, what do you understand by that?
Sir, like for calculating XP dash, we could have done summing up all the oversized mass fractions till that row which was mentioned 1.65.
Yeah, but if we do by the conventional way, if we define based on the cumulative mass fraction, because okay, first you answer this one. What do you understand if I say that cumulative mass fraction corresponding to the particle size 1.5 millimeter?
Smaller than 1.5.
Right. So all the particle mass of all the particle that are having size smaller than 1.5 millimeter. But what
So
do we
that is
want?
our reject. Uh,
That is our reject. But basically, that is our reject. What is our desired product is exactly opposite. We want the total mass of particle which is bigger than 1.5 millimeter, right?
yes, sir.
So if I define the smaller mass fraction as xp dash, then what would be yp? Yp, the way we defined it, the mass fraction of our desired product in the product stream. How this is related with xp dash?
One minus XP dash.
Yes, exactly right. So by definition, this xp dash, similarly the xr dash, are the total mass fraction of material having size less than 1.5 millimeters, because that is the definition of your cumulative mass fraction. That is how we defined it. We always go from bottom in the product and reject respectively. So the total mass fraction of the material having size greater than 1.5 millimeter, that is plus 1.5 millimeter, in the product and the reject stream would be exactly 1 minus of that. That is 1 minus xp dash and 1 minus xr dash. Remember during the last class or maybe last to last class, I told you like for some of the problems, if we go in a reverse way, like if we do the cumulative analysis from top to bottom, it helps. So this is one of the example, like where you, if you instead of doing the cumulative analysis from bottom to top, this will help you, because whenever oversize is the product, these things will help you. But that is not the way the cumulative mass fraction is defined. Cumulative, there is a standard. The standard way of defining cumulative mass fraction is, it is always defined as the total mass fraction of particle which is having size smaller than that specific particle. Okay, now what is yp? Sorry, what is yf here? Mass fraction of your desired material in the feed stream.
25%.
Right. So YF is 0.25. Is that clear to everyone? If not, just Ask me. Because why? See the problem definition. It says that excess fine content is 75%. So obviously 1 minus 75, 100 minus 75, that is 25% is your desired product. So the mass fraction would be 0.25. Now you tell me how should we proceed? So we know now, we know what is YP, what is YR. We don't know what is YP, what is YR. That is something we had defined. So, and YF we know that is equal to 0.25, and we have this table. So how should we proceed?
So we can calculate YP as 0.143 plus 0.211 plus 0.230.
And then you wanted the YP corresponding to particle size 1.5, right?
Yes, sir.
1.5 is not 1.5 is not here in this table. Then what should we do?
When interpolation.
Yeah, linear interpolation is something which is not desirable. I told you in the last class, that's why we do something else. What we do? Because that can lead to significant error.
graph, that regressor graph.
Yeah, that which type of analysis we should do here. So we learned two analysis, right? One is differential, one is cumulative analysis. So which type of analysis we should do here? Remember the
Cumulative.
Yes, remember the advantage of doing cumulative analysis. That is what I discussed. Like if you wanted to find out a specific fraction corresponding to a specific size, you can directly get it from the cumulative analysis. And that is what we want here. Okay, so how to construct the cumulative table here from the table which is given here?
Sir, we could try that log plot as well.
Yeah, what log or semi log or normal graph, that is the way you represent. That's not a matter problem. But how to construct this table, the cumulative table? So remember, in this cumulative analysis, we have constructed one table. This is the cumulative fraction smaller than DPI. How we did that? So we keep on
Sir,
adding
from
the
bottom to top.
Yeah, so
Yes, sir.
basically we can do the same thing here. We can add it up from the bottom and we can get the cumulative fraction. And if we do that, we will get a table which would look something like this. Because I had defined the cumulative mass fraction, the function xp for product and xr for capital XR for reject. So you will get something like this if you start from the bottom and go up to the top. Obviously, the top one will always have 1. Another tricky question. See this reject. So why you have 1 in here and here also? Can you comment anything that on by looking into this table? Okay, by looking into the table only, can you tell me the weight of particle which is having size 2.36 millimeter in the reject stream? What would be the weight? Listen to my question again. The weight of particle, the total weight. I want the total weight of particle which is having size equal to or greater than 2.36 not 2.33, equal to 3.33 millimeter. The top one.
So all the particles I think have size, as you said. So like it would be equal to the feed.
No, my question is, what would be the total
Zero.
weight of? Right, absolutely right. So it would be 0. There is no particle which is equal or bigger than 3.33. So that's why you have 1 plus 0 is equal to 1, because we keep on adding from the bottom to top. Now what we will do, we will plot this x with this particle size, right? And if we plot it, we will get a graph something like, which would look something like this. One is for the undersize and one is for the oversize. And oversize is what? Oversize is our product here, and undersize is our reject here, right? So this one correspond to this graph, and this one correspond to this blue graph. Now what is the next step? What should we do?
Sir, we draw a vertical line from X particle size 1.5 and check where it intersects the undersize and oversize curves.
Yes. So let's do that. So I had already marked 1.5 here in the graph itself. You can see here. So let's draw a vertical line from here. So if I draw a vertical line from here, where should I intercept? In this graph or in this graph? The reject graph or the product graph?
Product graph.
Why not reject? If I hit the reject graph and get the corresponding mass fraction value here, what I will get?
%75.
No, this is reject graph. This is not the graph corresponding to your feed. So there is
Yes.
3 mixture. One is for feed, one is for undersize, one is for oversize. Feed, we are not doing anything because XF is already given directly. We are only consulting about the oversize and the undersize graph. Now the way I had defined this XP dash and XR dash, see the definition XP dash and XR dash. XP dash and XR dash be the cumulative mass fraction corresponding to the particle size 1.5 millimeter. Right, now we are trying to draw a vertical line from here, which would hit the product and go here, and which would also hit the reject and go here. So if it hits the reject line, and correspondingly value that we will get in the y-axis, what will that be? Okay, let's draw the line. Let's draw first one line which will hit to the product line, and then we try to get the corresponding y value. So what would be this value? What is this value? Around 0.5 something, 5.9 or 5.8. What would be this value?
So the product mass function in the product stream, product mass fraction.
Product mass fraction, you are close by. It's the mass fraction of your desired material in the product stream. Is it the mass fraction of your desired material in the product stream? That is my question. See, what is your desired material?
No,
you
sir.
tell me. Our desired material is plus 1.5 millimeter particle size, right? And what we will get from here?
XP bar.
Right, absolutely right. This will correspond to XP bar. So this is what? This is a cumulative mass fraction corresponding to a size of particle size of 1.5. And what do you understand by cumulative mass fraction correspond to particle size 1.5? That is all the particles, the weight of all the particle or the mass fraction of all the particles that are having size smaller than 1.5 millimeter size. And that is what we said is the definition of xp dash. That is how we defined it. Now, see, if I go in a similar way and hit the reject or the undersize distribution and get the corresponding y value, what would be that?
XR dash.
Yes, this would be equal to xr dash. And we had already concluded that xr and how xr dash and yr is related and how xp dash and yp is related, right? That is basically 1 minus of that value. So from the graph we got this xr value, this xp dash correspond to 0.57 and xr dash is equal to 0.85. So what would be yp here?
0.43.
And yr would be equal to 0.15, right?
Yes.
Now you tell me what is the efficiency of the screen. You refer to the formula that I had used in the last class. So now we know yp, we also know yr. And yf we already know it's equal to 0.25. Again, if you see the value yf, yr and yp, the example that I had given in the last class, now does that make sense? See the yp value is 0.43, yr value is 0.15 and yf is 0.25, right? See, this is exactly similar to what we had discussed in the last class. So your yp would have the more or less highest value. In general, this is the standard norm. You can have exception. You will see in the next problem itself. If you have the mass fraction of your desired material in the production should be high, and that is why it's 0.43. And your mass fraction of your desired material in the feed stream would be relatively low, which is 0.25, and it would be substantially low in the reject stream, which is equal to 0.15 here. Now you tell me the screen efficiency. Yeah, this formula. Use this formula. Please, anyone, just give me an answer.
0.447.
Okay, 0.447. One answer I got. Anyone else? Same or different?
Sir, approximately 0.486.
0.447 and 0.486. That is too much of deviation. One has to be wrong.
Point 447.
Okay, 2.447.
Oh yes, sir. I did mistake.
Yeah, it's 44.75. I also got the same.
Sorry, sir.
Yeah, so 44.75. That is the effectiveness of the screen. So what you can comment looking into this number, looking into the efficiency of a screen. Is it low, high, or okay, or like if we think of an efficiency, is it a low value, is it a high value, or is it a something which you thought is fine?
So like it depends on which like what is the standard efficiency?
Standard.
What are the practical values that we actually
Yeah, I mean, just think in a layman perspective. You don't have any idea. You just see the number 44.
It is a low value.
It's
Yes,
a low
no,
value. Yeah,
very
it's
low.
obviously. I mean, if you don't think very in a complex way, you will just see that okay, this is a very low value, which is a fact. This is a low value. So that is all the operation that you will encounter in this course. You will see the efficiency of most of the processes are very low. And screening is one of them. Now you think of an industry process of the entire industry where screening would be one of the unit operation. Obviously, all the unit operation will contribute to the efficiency of the entire process, and this is something which will substantially pull down your efficiency of the entire process. And in terms of cost effective, this is also not a very cost effective process. We will solve one problem in the crushing and grinding, then we will see how much cost is involved in crushing, grinding and separation of particles, and how low the efficiencies are. This is a substantially low efficiency value, and this is something which is a very normal case in industry. Okay, another problem. Okay, we will start this problem and let's see if we can finish up this problem. Otherwise, I will finish in the next class, because next class you have the class test, right?
Yes, sir.
Next Thursday is the class test, and syllabus is up to sheaving. So sheaving will finish in this after I finish up this problem, and then I'll just show you some industrial screens. Those are just videos, so you don't have to remember anything on that. So let's read this problem. Table salt is being fed to a vibrating screen at a rate of 150 kg per hour. The desired product, here the desired product is a fraction. In the previous problem, the desired product was everything which was above 1.5 millimeter size. Now the desired product is a fraction, which is minus 30 plus 20 mesh fraction. Yeah, just which standard of screen is this one? Minus 30 plus 20.
Indian.
Indian.
Yes. So for performing this operation, a 30 mesh and a 20 mesh screen is therefore used. It's a double deck screen. So you have two screens here instead of one. And the feeding is introduced on the 30 mesh screen. Now during this operation, it was observed that the average proportion of oversize, that is the amount of material from 30 mesh screen to the oversize from 20 mesh screen to the undersize of the 20 mesh screen is equal to 2:1.5:1. Now what you have to calculate? You have to calculate the effectiveness of the screen from the following data. I'll show you a pictorial view of the entire problem, then you will understand in a better way. So your desired product is minus 30 plus 20 mesh fraction, and to get this product we are using a double deck screen, which is, and the top screen is 30 mesh and the bottom screen is 20 mesh screen. So we're feeding the entire material on the top of the top screen, and this the entire assembly separating the particle into multiple fractions. What was observed? It's a continuous process, as you know that the industrial screening is a continuous process. So at any point of time, the amount of oversize that you get from the 30 mesh screen to the amount of material that you will get as an oversize from 20 mesh screen to the amount of material that is there as an undersize of 20 mesh screen, that ratio is 2:1.5:1. Now what you have to calculate? You have to calculate the effectiveness of the screen from the following data. Remember, effectiveness of the screen is always based on your desired product. So here your desired product is this one, the 30 minus 30 20 plus 20 mesh screen. So how effective your entire assembly or entire screening process is to separate this fraction of particle. Based on that, the efficiency of the assembly will be determined. So I hope now you can understand how we construct this table. So you take the entire feed material which is fed to the screen, do a sieving analysis, and you will get this data. Take the entire material that you obtain from the oversize of 30 mesh screen, do a screen analysis, do a sieve analysis, again you will get this data. Whatever you obtain from the oversize of 20 mesh screen, again do a sieving analysis, you will get this data. Undersize of 20 mesh screen, do a sieving analysis, you will get this data. Let's show it pictorially, then you will understand the entire process. So as per the problem, it's a double deck screen, so you have two screens, one is 30 and one is 20. Which one is 30 and which one is 20 here? Top one is top screen is what? So here in the picture you can see it's a two screen. One is this one and one is this one. So if I say the mesh number of the top screen is, then what will be the mesh number of top screen? I can see the problem. It's minus 30 plus 20 mesh screen. And it's an Indian standard. So what will be the mesh number of the top one?
20.
Which one would be in top? Minus 30 plus 20. Okay, first you tell me what do you understand by this minus 30 plus 20?
That means they're undersized 30 and oversized.
Oversize of 20.
Yeah.
Undersize of 30 means?
That if the size is 30, like then the particles which are lesser than 30 will pass through that sieve, and it will not be able to pass through the one which is 20. So
okay, right, you're right, absolutely right. And here for achieving this fraction, we are using two screens. One is 30 size, another is 20 size. So which one we should put at the top?
30.
Obviously 30 will go to the top, because when minus 30 and plus 20, you are saying 30 is the screen which is having bigger opening, because it's an Indian standard screen. So it should go at the top. So this one is, the top one is 30 and the bottom one is 20. Right. So this is the 30 mesh screen and this is a 20 mesh screen. Now where is our desired product? Our desired product is minus 30 plus 20. Yeah, that is our desired product, minus 30 plus 20. Now looking into the picture, can any one of you tell me where is our desired product? So our desired product will come here, here, or here?
Left side.
Here.
Yes, sir.
Okay.
Yes,
Anyone
sir.
else? So here means it's this fraction basically, right? This fraction is coming out from here.
Yes, sir.
Now go back and see this table. It has three components. One is oversize from 30 mesh screen. So what is oversize from 30 mesh screen? Which one? This one, or
Right.
this one, right? So if I take this fraction and do the sieving analysis, I will get this data. Second is oversize from 20 mesh screen. Which one is that?
Second layer.
Left one.
Yeah, this one. And what was the last one? This is the undersize of the 20 mesh screen, right?
Yes, sir.
And this one is the feed. So that's why you have 4 columns. One is for this one is for this one for this one, and one for this one. That's why you have 4 columns, because this is the sieving analysis of 4 different mixtures. All are mixtures. I tried my best to make it pictorially more reasonable, so that you can see that here you have more red particles. That means, but you will obviously get some blue and some greens. Here the chances of red particle passing through is substantially low, so I ignored that. But obviously the blue and blue are the middle one, and the greens are the smaller one. So this mixture you will get here. and eventually the smallest particle will come down here. So if I try to mark all these streams, what I'm doing, I'm marking this one as feed, and this fraction is minus 30 plus 20. Obviously the mixture that is passing through 30 mesh screen but retained on a 20 mesh screen, so that is minus 30 plus 20, and this one is our product. This is same thing because we are getting the product from here. So we can mark this as one reject and this as another reject, right? So I'm marking this as R2 and R1. This is one reject and this is another reject. Fine. Is the problem description clear?
Yes.
So what we have to do, we have to find out the screen effectiveness or screen efficiency based on how efficiently the entire assembly separate this mixture, because this is our product. So for finding out the efficiency of any screen, first aim is to identify what is our product. Unless and until you identify your product, you will not be able to specify the efficiency of that specific screen, because the efficiency will vary depending on what your product is. Yeah, now to find out the efficiency, what values we need? We need all those y's, yp, yf, yr, all those y's we need. Those y's are what? Y's are defined as the mass fraction of your desired material in the respective streams. So we need yp, yr, and yf. Right. Look at this table. By looking at this table, can you directly identify what is yp here? Let's start with yf. What is yf here?
0.281.
Okay, 0.281. Anyone else? Anyone else has any other thoughts, or all of you agree that it would be 0.281? If you have other thoughts, you can convey. That's not a problem. Okay. Now what is yp?
So 0.526.
This is, you are saying, this is what you are saying as yf, and this is yp, right?
So this is the cumulative table, right?
This is not a
No.
cumulative table, but do you need a cumulative value here? People get confused here, so it's a very valid question.
So we don't need cumulative, right? Because it's only a range. So
yeah, because this is our product. So we don't need a cumulative value here. In the last problem, we need a cumulative value because our product was all the materials which were above 1.5 millimeter of size. That's why we need a cumulative value here. But here the product is a range, right? Is that clear to you that why we don't need a cumulative value here? Because our product itself is a
Yes, sir.
fraction. It's not the a range. It's a fraction only.
Yes, sir.
So that good part of this problem, we don't need YR here. Only using these two values we can solve it, because we will be using the other information. How, just see. So this is, we agreed that this is YF and this is YP. Now, if this is YF and this is YP, we can directly use this formula to solve this specific problem. This one. Question 4. I mean, you can use this one also. You can use this equation also, equation 7 also. But equation 4, you can use to solve this problem. How? Just see. So I'll be solving this problem using equation 4, and I'll leave it up to you to solve this problem using equation 7. Because see, there is another information which is given, the ratio of these three things. Now, what is given there? The proportion of oversize from 30 mesh screen, oversize of 20 mesh screen to the undersize of 20 mesh screen. So if I go by this naming convention, what I can say? Oversize of 30 mesh screen is what? R1, right? Oversize of 20 mesh screen is what here?
P.
P. And undersize of 20 mesh screen is R2.
R2.
It is the ratio of these three things which is given here. Now your entire feed would be addition of these three. So capital F is equal to R1 plus P plus R2. Agree, because whatever we are feeding here, that is divided into three parts. So R1 plus R2 plus P would be equal to F. So that is what I have written here. And what is given here? R1 is to P is to R2 is 2 is to 1.5 is to 1. That is what is given in the problem. Oversize of 30 mesh screen to the oversize of 20 mesh screen to the undersize of 20 mesh screen. This is what is given. So P by F, if you look back that formula, there you had P by F. P by F would be equal to P divided by addition of these three. So if I go by the ratio, this would come as 1 by 3. Now you directly put that in the formula, you will get the efficiency of the screen as 48.6%. I'll share the slide, just check the solution again. And if you have any question or any doubt, I can discuss that in Tuesday's class. So Tuesday's class, I will not start anything new. I'll just discuss some of the videos and images of some of the industrial screen that we'll see. That will be a very brief class, because Thursday we have the exam, and whatever doubt you have so far, everything we had discussed, just come up with all your doubts in Tuesday's class. Go through the solution, go through these problems. So one you can see there's two problems I have solved. One is based on the cumulative approach, another is directly taking the data from the table itself. Right. So that's it for today. So if you have any questions, you can stay here and ask the question. Otherwise, you can leave.